I'm Stephan Rosswog. I'm working at the Department of Astronomy in Stockholm. And I will talk about, well, multi-messenger astrophysics of merging neutron stars. And I think this is really one of the very hottest topics, well, that is around at the moment and probably will stay one of the hottest topics for quite a while to come, I would think. And as I've said already, we're talking here about neutron stars. And I want to just introduce a couple of the basics there. And first of all, you probably know this, neutron stars are born in core collapse supernovae. And we know many of them. So there are thousands of pulsars that have been observed. Many of them are actually in multiple systems. We have of the order, probably a bit more, than 20 double neutron star systems. And so far, there's no neutron star black hole system that has been observed. Now, for many of the things, just to get a flavor of the order of magnitudes, it's very important to have some feeling for the masses. And this is about 1.4 solar masses for a typical neutron star. And such a neutron star will have a radius of about 12 kilometers. And then you can just do the very simple mass. And then you find, well, the densities, the average densities actually, of those neutron stars can be well above nuclear matter density, which is about 3 times 10 to the 14 grams per cubic centimeter. And in the centers, of course, you can be much higher than that. Another thing that is very important is these are, of course, strong gravity objects. And just to illustrate this, if you just take a simple estimate for the gravitational binding energy, then you find that this corresponds to about 20% of the solar mass times c squared. So this is an enormous amount of energy. Well, this is a couple of times 10 to the 53 ergs. So this enormous amount of energy. And this is one of the reasons why initially one was very skeptical that such systems could eject any mass just because they're ridiculously strongly bound by gravity. Okay, now if you have two such stars, say a binary, these are really wonderful systems for both fundamental physics and for astrophysics. And first of all, it's not trivial to form them in the first place. So the pure existence of them tells us quite a bit about binary stellar evolution. And of course, the problem is if they're formed in supernovae, which produce kicks to the neutron stars, it's non-trivial that such a system survives these two explosions. Now, another reason why they are very interesting is that we have good chances to learn about high density nuclear matter. And there are regions that you can probably only get by such systems and by nothing else that I'm aware of. There are, of course, major sources of gravitational waves. That's part of the reason why we talk about this here. And also already in the 80s, Bernard Schutz realized that you can actually do cosmology if on top of the gravitational wave, you have also some electromagnetic signal. And one reason why we're all here is that they have been suspected for quite some time that they could be interesting sources of nucleosynthesis, in particular of rapid Neutron-Capture nucleosynthesis. And if this is true, then of course they would be related to the enrichment of galaxies. These freshly formed elements would produce radioactive flashes, which are sometimes referred to kilonovae. I refer to them as macronovae, but it's the same thing. And they have also been suspected to produce cosmic explosions that produce short bursts of gamma rays. And much of this was based on, well, just theory or indirect arguments. And then in 2017, the magic event has happened, the first gravitational wave detection that was also seen in electromagnetic waves. And it has really connected all of these areas. And we have learned a lot about all of these areas and actually much more. So what has happened was there was, well, a neutron star merger detected by LIGO. And you hear here the LIGO signal, the increase in frequency, and then bang, the gamma ray burst 1.7 seconds later. And this was, of course, something that one had always hoped for, but didn't dare actually to hope for it. And the punchlines were obvious. First of all, as expected, yes, they really do produce gravitational waves. And second, they also actually produce short gamma ray bursts, which was always an open question, plausible, but not proven. And in this particular case, it was actually even possible to locate the source. So the first thing that has been seen was Fermi. And here you have the error box from Fermi, which was this gamma ray burst instrument. And then Fermi, together with integral, restricted the region where you should look for the source in the sky to this area here. Then there was LIGO, and LIGO itself produced those green bananas here to search for, and Virgo has not seen it, the other gravitational wave detector. Therefore, it must have been here. And then there was a gigantic electromagnetic follow-up, searching for possible signals from this neutron star merger event. And it turned out there was, in this galaxy, there was then really a firework of electromagnetic radiation observed. And this event was probably one of the biggest electromagnetic observation campaigns ever in astronomy. And this event has been followed in gamma rays, ultraviolet, optical, infrared, and radio. So really all across the electromagnetic spectrum. Now, one of the punchlines in our context here was that this event, you see it here. So this is kind of the electromagnetic afterglow of that merger in the host galaxy, that this changed in color. So you see just about a day after, well, just a few hours actually after the merger, this thing appeared blue. And after a couple of days to a week, the signal became red. So this is an interesting evolution from a blue to a red signal. And I give away, in a sense, the punchlines first before I explain them a bit later. And the punchlines are this blue event, or this blue signal, is produced by material that has a relatively low opacity. And the reason is, it means it just becomes transparent when it is still pretty hot. And the low opacity, as we know now, is produced by electron fractions, which, and I'll come back to this point, which is above 0.25. And this red signal is produced by some other material, which is high opacity material. And high opacity just means an expanding cloud of radioactive material where the photons have a harder time to escape. And that means they can only escape at later times when this cloud has cooled, and therefore it's, it's cooler and therefore redder. And this type of material is produced by electron fractions which are below 0.25. And this is a very important punchline for this whole event, in particular in the context of forming heavy elements. So, and the punchline here is, well, this can be explained and was actually expected before the event from freshly synthesized R process elements. And one thing that has been also observed and was maybe not not most people's best expectation is that strontium has been observed, and I think Camilla will explain this in more detail later today. So in a sense, this thing delivered essentially everything we could ever have asked for. It gave gravitational waves, it gave short gamma ray bursts, we knew the host galaxy, electromagnetic follow-up, the Hubble parameter could be determined, the speed of light, the propagation speed of gravitational waves was constrained to an enormous precision to the speed of light, which was very important for constraining alternative theories of gravity. We got constraints on how nuclear matter behaves at high densities. And then there was this radioactively powered transient, which showed, well, that neutron star mergers are at the very least a major source of our process, likely actually the major source of our process. But of course, there are still a couple of open questions. Now, this has been named by the Science magazine the breakthrough of the year 2017. And essentially, most of this comes from really the combined detection of gravitational and electromagnetic waves. So this is really the clue, this combination of these two different messages. So, and the gravitational waves, from them we can learn about the system masses and the spins and how they deform before merger. And the physics that actually determines this signal is relativistic hydrodynamics. Its density it's the equation of state at densities above nuclear matter density. So I'm always using this EOS for equation of state as an abbreviation. And of course, strong field gravity. While electromagnetic emission, that tells us about the host galaxy. It can tell us about the redshift of the host galaxy. Also, the physics that impacts what we see is a different one. A lot of this is shaped by weak interactions, by the nuclear reactions. In the end, the electromagnetic signal relies on, well, the atomic structure and proper radiative transfer calculations. And one thing that I actually also want to stress is the gravitational waves. They are determined essentially by the bulk motion of the material. So what the bulk of the matter is doing shapes the gravitational wave signal. You don't see much of tiny little matter pieces that are flying around. And say the composition has a very minor impact. It only if it changes the equation of state and makes it, for example, softer or so, would you see any impact of the composition. Now, this is very different for the electromagnetic emission. There, whatever you see has been produced by a very small fraction of the system mass. So this is just about 1% of the binary mass. And here the detailed composition is really crucial. So this makes all the difference, well, how this would look like for an electromagnetic observer. And maybe also just to mention this briefly, say, depending on which question you're asking, you would probably implement different types of physics in your models, and you may actually even want to change, or maybe actually even want to choose a different numerical method to do so. But that is an entirely field in itself, and I will not talk about this. So now I've said, well, we have seen these two signals. We have seen the gravitational waves and the electromagnetic ones. And it's important really to realize that these are two different things. So the gravitational waves, this is produced on length scales of, say, 10 kilometers, so something like 10 to the 6 centimeters. The time scale for the merger itself is milliseconds, while for the electromagnetic signal, you have distances. This is happening at something like 10 to the 15 centimeters, and the time scale is really days or actually weeks. Now, as you can imagine, the big question is then, well, actually, what is happening in between here, going from the gravitational waves to the electromagnetic waves? And this is, there's, of course, a lot of very, very exciting physics and astrophysics in between. So just one thing that can keep you busy for many decades is modeling the merger itself. And that means you need to have gravity right, you need to have nuclear matter right, you need to get you need to model the hydrodynamics. And as I will stress a little bit later on again, weak interactions and neutrino emission and neutrino transport are really crucial for what comes out, potentially magnetic fields, and so on and so forth. Once you have done your best possible job here, you would know the mass, the velocities, and the electron fractions of the ejector. Once you know this, then you can start doing your R-process calculations, where you need to have all kinds of nuclear physics inputs. So you need to know about, for example, alpha decays, neutron captures, fission, all these type of things. Then once you have done this, then you have a cloud that is expanding, and radioactive energy is continuously pumped in. And then you want to know, well, how much energy remains in that cloud? And how does the cloud expand, for example, in reaction to this? And then once you have this, you can start your radiative transfer calculations. And for them, you need to know the atomic physics. You need to know what are the lines in those elements that you have, which give you the opacities, and so on and so forth. And once you have that, then you can start your comparison with what has actually been observed. So you see, there's a lot of exciting stuff in between. And a lot of very good work has been done there over the last, let's say, 2 decades or so. But of course, there's plenty of room for further improvements. And I would highly want to encourage you to, if you find this type of stuff interesting, please help us to make these models even better and learn to understand even better what is happening between those two observed things. Okay, so now I want to, as I said, it's a bit a reverse engineering process. I first gave you the punchline from the observation. Now I want to say a couple of things about the generation of gravitational waves. And they are produced, in a sense, in some respects, similar to electromagnetic radiation. The key point is you have a finite propagation speed of a signal. But contrary to electromagnetic, emission, you are not dipole emission, for example, to lowest order. You have just one mass with just one sign, and the mass is conserved and the momentum is conserved, and that forbids monopole or dipole radiation. That means to lowest order, what is producing gravitational waves is a time-changing quadrupole moment. And once you know this, you can work out what the gravitational wave amplitudes are, and I can come back to this in a second. And this is, as you see here, it's given by the second time derivative of this quadrupole moment. And the very important thing is that the amplitude dies off with 1 over the distance. So this is important to keep in mind. It only drops off linearly. And that is, of course, good if you want to detect this. If it would drop off, say, quadratically or something like that, then it would be much harder to detect. Now you see, we can also work out the gravitational wave amplitudes, the luminosities. And they are given now again by this quadrupole moment. And now it's the third time derivative. And you have here a contraction of the third time derivatives here of those guys. And those quadrupole moments, they are just calculated, just what you have likely seen in classical mechanics. It's in this approximation, it's really just the Newtonian quadrupole approximation given by this formula. Now, one very important point to keep in mind is you have this prefactor here. So this is G, which is the gravitational constant, which is a very small number. And you're dividing by a very large number, the speed of light, but not only the speed of light, but you actually take this to the 5th power. So this prefactor is enormously small. So in CGS units, this is about 10 to the minus 60. And that means if you really want to get an observable signal, then those time derivatives of the quadrupole moments, they should better be large. So otherwise you have 0 chance. You need something with a large change in the quadrupole moment. Now, of course, calculating this in detail can be pretty complicated, but you can start as often with simple order of magnitude estimates, and they give you already a very good insight on what are interesting sources. Now, if you just go back to the previous slide and look at the formula for our quadrupole moment, and then you just think about its dimensions, then you see, well, it is something like a mass times the length to the power of 2. And now let's keep in mind, let's assume we know something about our source that we're interested in. Let's assume it has a typical mass. Let's assume it has a typical velocity. And let's assume it has a typical size. Then you can estimate the second time derivative of that thing by, in a sense, just taking this one here and dividing twice by typical length scales. And of course, this is then giving you a mass times the velocity squared. And for the luminosity, we needed the third derivative. Then we have to divide by yet another of those length scales, which of course you can always construct by the velocity and the radius. And then you get this thing here, the mass over the radius and the velocity to the third power. And now this quantity mass over radius, this is something that in relativistic astrophysics is called the compactness. So this is the quantity that decides how important relativistic effects are. So say in the, in our solar system, typical values of these things at the objects are 10 to the minus 6, but say a neutron star can have 0.2, so gigantically much larger. And this will come up again and again. Now, that means if you just look at these estimates, that tells us, well, we would want to have a large mass that is moving, well, ideally close to the speed of light. Now, we're talking about self-gravitating systems. And for a self-gravitating system, the velocity is actually related to the gravity of the system. And this is this famous virial theorem that maybe you have heard about in your classical mechanics lectures, or maybe in an introductory astrophysics lecture. And the punchline is the kinetic energy is of the order of the potential energy. If you look at this more detailed, then there's a factor of 2 involved, but just for our order of magnitude estimates, that's good enough. And that tells us, well, once we know the gravity of the system, we know the typical velocity. And that means we can just solve this one here for the velocity, which gives us this gm over r. And now maybe this rings a bell for you. Say, oh, GM, that was something. Yes, this is the Schwarzschild radius. If you have 2 GM over c squared, and now you can just plug in the Schwarzschild radius into this approximation here, and then you find, well, the velocities are given by something like the speed of light, and then you have a factor which is the Schwarzschild radius over the size of your object. And that means if you have a very compact object, then you can actually reach velocities which are substantial fractions of the speed of light. Now, of course, you need you need an object that is not too different from its Schwarzschild radius, and there are not many objects around. So these are essentially really just neutron stars and black holes. And in that sense, compact binary sources, compact binary mergers are kind of ideal sources. Like just before merger, you have something like 3 solar masses, and these guys are going around each other at about 10 or 20% of the speed of light. So this is really the kind of thing that produces these enormous changes in the quadrupole moment. Now, you can now do the same thing, just to set the estimates from before. Now express everything in terms of compactness. And then you see, well, the amplitudes of the gravitational waves, they're proportional to the compactness. Again, so this comparison between size and Schwarzschild radius. And the luminosity is even actually more extreme. This is compactness to the 5th power. And now I've written it in this way. And then you see, if you write it this way, then you have a prefactor here, which is now c in the nominator, but to the 5th power and divided by a small number, the gravitational constant. And that means this prefactor here is about 10 to the 59 ergs per second. And just to compare this, the solar luminosity is 4 times 10 to the 33. So you are about 26 orders of magnitude larger in the luminosity than the sun. So this is something like an upper limit that you could potentially reach in a gravitational wave event. And some people have actually given a name to this prefactor. They call this 1 Dyson because it's the absolute upper limit. But of course, a black hole merger can reach a substantial fraction of that. And the first event that was ever detected in 2015, the merger of 2 black holes, that produced a peak luminosity of about 4 times 10 to the 56 ergs. And this is of course just happening for a fraction of a second, but this is outshining really all of the electromagnetic luminosity in the whole universe. So for short amounts of time, these gravitational wave events can be enormously bright. Okay, now coming back to the neutron star mergers and neutron stars. We know a couple of those systems, and the maybe most famous one is the Hulse-Taylor pulsar, which was the first system that was ever detected. And here's a little sketch how this would be relative to our sun in the Milky Way. And then there's another system which has become an even better laboratory for gravity, which is called the double pulsar. And the name is coming just because both of the neutron stars are active pulsars. And to just give you a flavor of the relativistic effects in those systems, there is this famous perihelion shift of our planet Mercury, which was one of the first strong evidences that general relativity is a good theory, and that is 43 arc seconds, this perihelion shift per century. So just in 100 years, only these 43 arc seconds. Now, if you look at these systems, the Hulse-Taylor pulsar has about 4 degrees per year, and double pulsar is actually even 17 degrees per year. So these are highly relativistic systems. Now, for the Hulse-Taylor pulsar, it has been monitored very, very well, and really from the beginning. This was a sensation, of course, once this was detected. And this is now a plot which looks a bit more complicated than it actually is. So here you have on the y-axis something which has the complicated name. It's the cumulative shift of periastron time. And here you have the time in years. And what this means is just you have an eccentric orbit, and you can now think of just measuring each time the system reaches periastron, and then you just monitor this time. And now gravity has this peculiar property that if you take away energy, the orbit becomes tighter and it gets faster. So in a sense, you're braking the system and the system speeds up as a response. And that means the system is reaching periastron each time a tiny little bit earlier. And this is an effect that piles up over the years. And this is what is shown here. If there was zero energy loss, then everything would be on this line here. And I think this is really an amazing plot because you see here these black dots. And what you probably do not see is that these black dots have error bars. And another thing that I find very impressive is that the line that you see is actually not a fit through the data, but that is actually the prediction from general relativity. And in this limit, you can do this all analytically. And the agreement is really excellent. And this is what has given Hulse and Taylor the Nobel Prize in '93. And of course, this was one of the major motivations to build a gravitational wave detector such as LIGO, because otherwise people would probably not have trusted in the existence of gravitational waves. Okay, now about the in-spiral. And this is now getting closely related to nucleosynthesis and chemical evolution. This in-spiral can be calculated, and it is given by this in-spiral time. And here you have it in terms of the orbital period of the system and in terms of the eccentricity. And well, you see now it actually depends on very large powers of both of them. And if nature would only produce binaries of one given orbital period and one given eccentricity, then you would, of course, expect just only something like one in-spiral time. But binary evolution is a very complicated thing. So nature will produce a broad range of orbital periods and a broad range of eccentricities. And that means you have to expect a broad range of in-spiral times. And this is a plot, again, which looks maybe a bit complicated. So this is now this orbital period in hours. And this is the eccentricity. And what you see in colors is the in-spiral time. So just this tau GW. And you see, well, those systems that we had talked about, the Hulse-Taylor pulsar has about, well, 3 times 10 to the 8 years. And the double pulsar has somewhat smaller in-spiral time down here. But you can also now just think of, assume your double pulsar would have a high eccentricity. And this is actually not crazy. This is actually likely because it has to survive 2 supernova explosions. Assume this would be 0.8, then you would be here. And then the in-spiral time would be about 1 million years. So you really have to expect both short and long systems. And the ones that you see are, of course, the long ones because they're more likely to be observed. Okay, now coming to the electromagnetic emission. So I've said it's just 1% of the matter that we're talking about. And I've said the composition is really crucial because it determines the nuclear heating rates and it determines what type of elements we have and what the opacities are. And for that, we really need to understand, well, the properties of this ejector. And that means, first of all, of course, we need to know, well, how much do we have? What's their geometry? What's the velocity structure? But in particular, also, what are the weak interactions that are going on during the merger? What is the nucleosynthesis? And then the radiative signature, of course. So now we are coming to the nucleosynthesis, and we are talking here specifically about the rapid neutron capture. And just to briefly recapitulate this, if you look at the solar system abundances, then the lightest elements you would form in the Big Bang, well, up to maybe iron peak type elements. This would be mostly stellar burning phases. And the best way to form heavier elements is via neutron captures. And you see here this double peak structure. And this tells us essentially that nature is working in kind of 2 modes. One is a slow mode, which is these 2 peaks here. And another one is the rapid mode, which is the rapid neutron capture or the R process. And this is not just a tiny amount of elements, but this is really something roughly half of the elements that are heavier than iron. So it's really an important process to understand where these elements come from. Now you can, since we're talking about neutron star mergers, and I've just shown how complex the situation can be, you may wonder, well, what determines the elements that are formed? And the really most crucial quantity here is the electron fraction. And it's defined just as you can think of this as something like the number of protons over the number of nucleons. So if you have charge neutrality with electrons, then it would be the same as the number of electrons over the number of nucleons. And the punchline is, if you want to reach these very heavy elements up here, you need a very large number of neutrons per seed nucleus, and you need very low electron fractions. And if I say very low, I mean substantially below 0.5, but really substantially below that. And just in a cartoonish picture, the electron fraction would have a very big impact on where the nucleosynthesis is happening. So if you think of here the neutron-proton plane, and you would have the value of beta stability being here, then if you have a relatively high electron fraction, all the action would happen actually close to the value of stability. But if you have an extremely low electron fraction, you can do lots and lots of neutron captures and can really go up to the neutron drip line here. And you would have a lot of the nucleosynthesis happening close to the drip lines. So now the production side, the basic understanding of the R process is actually pretty old. That was the first seminal paper on that was from, well, the first two seminal papers was from 1957 by Burbidge et al. And by Cameron et al. And traditionally supernovae have been, well, the most popular production site. And but I've said there was this Hulse-Taylor discovered in the early 70s. And Latimer and Jim Latimer and David Schramm, they were wondering, well, maybe if these guys could merge and maybe if these guys could eject some material, then this would be interesting for our process. Problem was just at that time, you could, of course, not do any full-blown simulation, and they had to do some rather serious approximations. And they found as ejector amounts, well, something like 5% of a neutron star, but plus minus 5% of a neutron star. So it was clear that this could be very important if enough is ejected, but it wasn't clear whether there's actually anything ejected at all. Then there was an interesting paper which brought neutron star mergers together with our process and actually also gamma ray bursts in 86 by Eichler et al. And then we had done in 98 the first really simulations of merging neutron stars, where we also calculated the nucleosynthesis. And we found very nice results. Let's say our first well, conference proceeding came out in May 11, 98. And we had just found, well, what we find is ejected is just enough to, at least in principle, within the error bars, to explain all of the R process material that we have. And the other thing was, well, it produced very nicely the solar system R process abundances, in particular without any tuning, this third peak here. This is this platinum peak, it's also called, because platinum is sitting here. And we were, of course, very excited about that, but it was just our conference proceeding, and it took us a while to write it up. But some people, Lee and Paczynski, they had read this very carefully, and then they just asked the next question. They said, well, if this is true, then you should expect some transient. And these transients that they talked about is what people today call kilonovae or macronovae. And then our own real paper only came out after that, because it took us a while to write it up, since we were just young PhD students at that time. So now, in which sense would you now expect to see a difference between supernovae and compact binary mergers? Well, one thing where they're very different is the electron fraction. Say, in a supernova, you start from something like roughly the same number of protons and neutrons, so YE of about 0.5. While in a neutron star, you have a very low electron fraction. This guy is going down, so it's deleptonizing, while if you slam the neutron stars into each other, they heat up enormously and thereby do lots of positron captures and are kind of reprotonizing. There's also, for the chemical evolution point of view, a substantial difference. These occur pretty often, and they don't have to eject very much. Well, these guys are pretty rare, but they need to, if they should be important, they should eject quite a serious amount of material. And of course, also where the event happens can be very different. Mergers, since they have a broad range of these in-spiral times, they can either happen inside of a galaxy, or some can also actually travel outside of the galaxy, while supernovae are really predominantly in the plane of the galaxy. Now, I've said the electron fraction is the crucial thing. So now, what is the electron fraction in a neutron star? And this is a somewhat complicated plot. So what I'm doing here is I'm constructing a stellar model. So I'm taking a neutron star, solve my relativistic stellar structure equations for a given equation of state. And I assume that this is in beta equilibrium. And then I'm just measuring how much material do I have of which electron fraction. And just to make this more concrete, maybe let's just focus on this point here. So this means this is one particular neutron star with one particular equation of state. But this means that only about 5 times 10 to the minus 5 of the neutron star has an electron fraction about 0.07. So that means essentially all of the neutron star is below an electron fraction of 0.1, and only tiny fractions are above this critical value. And this is similar for different masses and different equations of state. So now what that tells us, well, I just had explained that this first macronova observation has told us we see a broad range of electron fractions in this macro kilonova. And that means what we're seeing is the result of the weak interactions that have happened during the merger. And they are really crucial for the nucleosynthesis and for the electromagnetic signal. And I think we will hear also more about the weak interactions by a later talk by Ina Kulman. Okay, so now what do neutron star mergers actually eject? And that is now also much more complicated than we thought in the early days. In the early days, we only realized about those tidal ejector. They are still a very important type of ejector, and they are at essentially the original electron fraction and maybe 1% of a solar mass. But you can also eject material from the interface between the neutron stars just when they collide. So this can have somewhat different properties. And then once you have formed such a remnant with a torus around it, this will emit enormous amounts of neutrinos. So similar to what you have in a core collapse supernova, so something like 10 to the 53 ergs per second. And this material or this neutrino emission will blow off matter from this remnant. So you have something like a neutrino-driven wind, but also for such a neutron star merger remnant. And then there's another source which is not as, at the moment, not as well explored as the others. And this is just this torus. This will evolve over time and over a relatively long time scale for such a merger. And this is a time scale of maybe a second or so. And on this time scale, a very serious fraction of this torus can become unbound. So this is yet another source of possible ejector. Now, just to illustrate this a little bit, so these are now those tidal ejector, those tidal dynamic ejector. And this is now just one neutron star system with a slight asymmetry in the masses. I have chopped off the upper parts of the neutron star so that you can see the electron fraction inside. You see here the time scales. So we're talking about really milliseconds. Now they come into contact, form a shear interface here, which becomes Kelvin-Helmholtz unstable. And then just the tidal forces eject this type of material. And you see, well, this is bluish here. And this is really then just electron fractions of the order of 0.05, flying out at about 15% of the speed of light. Now, the situation is actually pretty different for these neutrino-driven winds. This is now a simulation from Albino Perego. And all kind of things are shown here. Just please focus on the electron fraction, since this is the most important one here. And also to say this, the original orbital plane of the merger, this is what is shown here as z equal to 0. So this is this line here. And we're just showing the plane perpendicular to this. And now you see, as the movie starts, that matter is driven out along the original rotation axis of our binary originally. And now you see that the material that is ejected has, well, you can say, well, greenish, yellowish color here. So you see a lot of this material is well, in a broad range, which is very different from these tidal ejectors. So it's something like between 0.2 and maybe 0.4 or so, but a broad range of electron fractions and substantially lower velocities. Now, this has, of course, also pretty serious implications for the nucleosynthesis that is happening. So I'm just showing here as two extreme examples. So this one here would be a trajectory from this tidal dynamic ejector that I've shown first. And the other panel here is a trajectory from this neutrino-driven wind. And you see now these tidal ejector, they start here really at the neutron drip line. And here you see the current abundances. They go here to this super heavy region. And then at some point, material is decaying back towards the value of beta stability here. And then you produce a very robust pattern of these things. And again, I mentioned this platinum peak before. This is this one here. And you have essentially nothing below this 130 from such a trajectory, but a very robust pattern with this second and third peak here. Now, if you look at the neutrino-driven winds, that looks actually pretty different, just because the electron fractions are different. You see, you're not really at the drip line. You're never going into this super heavy region here. And once you end up with your final abundance distribution, this is also very different. So it complements this one here actually pretty nicely. But there's no second and third R process peak involved here. So these very heavy elements are missing here for this neutrino-driven wind, but it's of course still R process elements. If you do this slightly more systematically, then this is just a little experiment where you expand material, and the only thing that you vary is the electron fraction. And you see the solar abundances in blue here. The result of these network calculations are shown in red. And you see, if you're particularly interested in this heavy region here, you see this is done robustly up to maybe 0.2 or so. And then at a value of 0.25, this is really breaking down. You don't produce this region anymore. And you produce these lighter R process elements. So this is now very crucial, both for the nucleosynthesis, but also for this electromagnetic transient that you see. And the reason is that these very heavy elements have very different opacities, as I've said already before as a punchline. And these type of elements have opacities which are well of the order 10 square centimeters per gram, while these lighter R process elements have just a much smaller opacity. And this has really dramatic impact on the color of the transient that you would expect from that. Just to briefly summarize this, in some sense, those macronovae or kilonovae have some similarities to normal supernova. So you have radioactive material that is expanding, but it's much less material and it's much faster, and it starts from a very different composition. So if you think of this as typical supernova elements, maybe down here, and then neutrino-driven wind elements maybe up here, and then these tidal dynamic ejector, these may be really then elements in this region around platinum and so on. Now, just qualitatively, what would you expect? Well, I've said you have a cloud that is expanding and you have radioactive elements. So you pump in energy and it takes some time for the photons to escape, of course. And as the thing is expanding, a larger and larger fraction of the volume becomes transparent. And that means, well, the luminosity is increasing because you're seeing more and more of the radiating volume. And at some point, essentially a whole cloud is transparent. This would then mark roughly the peak of the luminosity. And later on, what you see is just the radioactive energy, or something proportional to the radioactive energy times the mass of this cloud, which is producing the luminosity. In terms of this Q dot, if you plot this is really just a cartoon, but just roughly, if you plot this as a function of time, then it's more or less constant for about a second. And then later on, you have a power law decay with this characteristic time dependence of -1.3. And just to summarize this, so the key ingredients are really, you need the ejector mass, you need the ejector velocity, you need the electron fraction. All of this is set by the astrophysics that you're doing. Then you need the opacities, which is set by your atomic physics. And then later on, you need things like the heating rate or, well, some efficiencies. And they're determined by the nuclear physics. And I guess Gabriel will talk more about this in his lecture. And so as I said, the expectations for this thing was if you have electron fractions above 0.25, then you expect a fast and blue transient. And if you have electron fraction below that, you would expect something which peaks much later and will be red. And this was actually the expectation before it has actually been observed. So now that brings me to my summary. And I really want to say, I think neutron star mergers are really literally gold mines to learn, not just because they likely produce gold, but it's really, they are really gold mines to really learn new physics and astrophysics, and really to connect really different pieces that have so far been very separate. They're extremely neutron rich, as I tried to explain, and therefore they're really the ideal starting point for heavy R process elements. And they produce, just because of this, the third peak without any tuning. And they eject a fair amount of matter, and actually even more than we thought from our early simulations. And therefore, they're at least a very important source, maybe the only one. Probably, I would say it's probably that other sources can contribute as well. Would be very, well, it would be very unnatural if just one single event produces all of them. And we have learned really from this macronova event that it produces a very broad range of both R process elements and electron fractions. And that means it's really, really crucial to understand which weak interactions are going on during the merger. So we really have to do the neutrino transport very accurately to get good answers for how this would look like electromagnetically. But of course, plenty of open questions like, do they produce the whole R process? Are they the only source? If not, what else contributes? And of course, questions about diversity, like how similar are different types of mergers? How different is a neutron star black hole merger? And so on and so forth. There are plenty of questions. But I hope in the next decade or so, we will get lots of very good answers on that stuff. And with this, I want to stop here. Thank you very much for your attention.
Thanks a lot, Stephan, for this very exciting talk, and also for encouraging everyone to stay in science or come to science and help studying these interesting questions. So I will now give to Andreas, who is moderating the questions. So Andreas.
Yes, Stephan, thank you very much. I have not so many questions, actually. I think people were a little bit shy to add, but I will go through them with you, and let's see whether you can answer them. The first question was, what is the current status of merger modeling? What are the challenges that the simulations are currently facing?
That is a very good question, and it's of course an ongoing question. There has been dramatic improvements, say, in the last decade, but of course there are, as the question suggests, there are lots of challenges, and one of them is it needs to be three-dimensional, fully general relativistic, but at the same time, it needs to ideally include magnetic fields, which are a pain in the neck. Also neutrino transport, and as I tried to stress, there is really this pretty sharp change in the abundances at this 0.25, and therefore the neutrino transport needs to be done very accurately. And neutrino transport has been done in the context of core collapse supernovae, well, for half a century. But still, these are really tough problems, and they're actually tougher for neutron star mergers, because there you cannot make many approximations that are good approximations in a supernova context, just because the geometry is way more complicated. So this is just the one thing. And the other thing is, of course, you really need to go, just to illustrate this in terms of density, if you want to bring together the gravitational wave signal with the electromagnetic signal, the gravitational wave signal is shaped at densities of something like 10 to the 15 grams per cubic centimeter. And the peak of this macronova or kilonova is happening at densities of something like 10 to the minus 16 grams per cubic centimeter. So you have of the order of 30 orders of magnitude in density. And of course, that's a completely different physics that is happening at 10 to the 15 gram or 10 to the minus 15 gram. And these are enormous challenges. The other challenge, just maybe, since I've not said anything about the numerical challenges, but I think as often in these type of problems, the numerical challenges are very closely related to the physical challenges. And these are exactly these things, an enormous range in densities, but also in the length scales, as I've shown, between 10 to the 6 centimeters to maybe 10 to the 15 centimeters, and also the time scales. If the neutron star wants to wobble on time scales of fraction of a millisecond, that means your numerical time step needs to be an even shorter fraction of that millisecond. But what you're really interested in is something that goes up to a week. And this is nothing that you can do in one go. So these are just some of these challenges.
Mm-hmm,
but of course, one could do just a whole school on just the challenges related to this.
Absolutely, yeah. We take the next question. Are current observations of gravitational waves from neutron star mergers sensitive to different categories of equation of state models?
That is a very good question. And I have prepared something which I've kicked off in the end because I thought I didn't have the time. So this is now one of the questions: what can you actually learn from gravitational waves to constrain nuclear matter? And today, maybe that seems very a natural thought to you, but at least when it crossed my mind the first time, it sounded like really a bit crazy to me to learn about nuclear matter from gravitational waves. But of course, these days, many people are used to that thought. And if you look now, this is now the characteristic strain. So this is what a detector could measure. And you see the sensitivity curves, for example, of advanced LIGO here. And the Einstein telescope, which is a future gravitational wave detector, would be here. And if you take a typical binary system, twice 1.4 solar masses, that would just enter the LIGO band at about 2 Hertz, say here, and then move over to that side. And for a good fraction of this, you can really treat this analytically, because the neutron stars, they're so small, they don't realize that they have a finite extension. They're far enough apart from each other, so you can just treat them really as relativistic point particles. And you can do this with, it's complicated and it's really nasty expressions which go over many, 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 many pages before the next equal sign shows up, but you can do it. And these are so-called post-Newtonian theories. And only once the neutron stars are so close that they are maybe a few times their own radii apart, then they realize that they are deformed. And this deformation depends on the equation of state. So this is kind of like, if you have the tidal field from the companion star, if you know the equation of state, that tells you how the star is deformed, and this will actually really have an impact on the gravitational wave signal. And from the first detection, there were constraints on this tidal deformability. So, and therefore some equation of state could be kicked out, but it's not terribly constraining. And what this is telling us at the moment is essentially just about the cold nuclear matter equation of state at densities which are roughly neutron star densities. So the next thing would then be the merger itself. That would be happen here at frequencies of maybe 3 kilohertz. And this is nothing that LIGO can see at the moment, just because here the frequency curves increases. And this is at the moment in the noise. But this is, of course, a very exciting region where you have many times nuclear matter densities. You have temperatures of, say, 60 MeV. So in normal units, this would be 6 times 10 to the 11 Kelvin. So this is 10,000 times more than what you have in the core of the sun. And also due to the weak interactions, this would be at different electron fractions. So this is really a completely new laboratory for this extreme matter. And here you can reach regions in the temperature density plane that I think are not reachable by any other means. So this is nicely complementary to what people try to do at heavy ion collision facilities, but it will probe a different range.
Okay, I think we have to go on. We have 2 more questions at least, and then we can maybe postpone a couple of questions for the roundtable discussions. Do we have a chance to find transients or remnants of transients in our galaxy?
That is a good question. And I would think likely not. And the reason is, say, a typical number is that you have such a merger in a Milky Way type galaxy every 100,000 years. So if something should have happened, a typical time for the age of that would be maybe something like 100,000 years. And then it would be very hard to see anything that can be properly identifiable with such a merger remnant. So I would think we would need a lot of luck, but let's let's not give us hope. We say after the first multi-messenger event, many people were way more optimistic than just a couple of months before. And one reason is nature has really essentially just delivered all of our wish lists. So maybe we're lucky again. I think maybe we shouldn't bet our life career on that. But we may be lucky, but I think it's not terribly likely that we can do this.
A related question that I had was 1708-17 a typical NSM event in terms of the properties and in terms of the distance, and what is the rate that we can expect for the future?
This is another thing, which is of course a question that we all have and that we don't have a firm answer to. But my judgment is that this is probably a very specific event, and a very extreme one in the sense that we were really lucky that it was so nearby, and we would never have taken the gamma ray burst seriously if it had happened just somewhere without the gravitational wave signal. And the other thing is, when we did our first merger simulations, we found that about 1% or so of material has been ejected in a merger. And at that time, people told us we're completely crazy because this is a ridiculously large amount and this will never happen from such a system that is so extremely gravitationally bound. It's just crazy. And now if we try to interpret the observations, we need actually a few percent to do so. There's of course still a bit of room because, as I tried to explain this, the modeling between the gravitational waves here and the electromagnetic waves there is extremely challenging, and there's certainly room for factors of, well, maybe a few, but at least if we take the best models and we take them serious, they would tell us that probably something like 5% have been ejected. And also that may be a specific event.
Okay. I would suggest there's a couple of more questions in the chat. I would suggest, since they are maybe a bit more specific, we postpone those to the roundtable discussion at the end. And I give the word back to Konrad. Thank you very much, Stephan, again for your talk.
Okay.
Thank you, Stephan.
Thanks again, Stephan.